little parts. So let's just take a look at the first part. Okay, let me set you up with this, because at first it looks kind of intimidating. This one is probably the most common way that you work Dalton's law. It's just not immediately obvious that it is a Dalton's law. Let's say we have a big container, some big bottle. Down here in the bottom, I have some zinc metal. Now, zinc metal, monatomic or diatomic? Monatomic. So just some pieces of zinc like you've used in the laboratory, those little shiny things. I'm going to put them under water just to keep them submerged. And they're not going to react with the water. And then I'm going to put in a super long funnel. What's the name of that stuff?
Hydrochloric acid.
Hydrochloric acid. I'm going to add some acid to it. Now, what could happen here? Well, you have zinc, which you've told me is monatomic, and I have hydrochloric acid in aqueous solution. In fact, you've actually done this reaction in the single displacement laboratory, and I gave that away. I was going to say, I was going to say first, what does this have the potential for being? What kind of reaction? Single displacement. Some of you were listening, or some of you know. It has the potential for being single displacement. If you did it in the lab, you saw, bubbles start coming up through there. Or if you're just doing a paper and pencil, we can always go to the activity series. And on the activity series, we see zinc is way above hydrogen, should kick it out. Could you predict what we get out of this thing? What would be our products if this goes?
Zinc chloride.
Zinc chloride. I want a formula. Zinc chloride.
ZeCl2.
Yeah, because let's go down here.
ZnCl2.
When zinc takes on a charge, it always takes on what charge for us? 2. It's non-variable. Good. And chloride, you know by position, it's always a minus 1. So Nina did a great job. You get zinc chloride, and yes, that is soluble. Rule 2, all chlorides are soluble except the magic 3. What else do we get out of this thing? H2. Not just H, but H2, because you know when hydrogens get together, they're going to be diatomic, and that's going to be gas. Okay, to balance this thing. 2 in front of the HCl. Okay, single displacement going to work. Okay, if this thing is sealed up, I'm going to have trouble. I want to collect the hydrogen because I know it's an explosive gas, and it'd be fun to play with. And so, how can we collect that gas coming off? What we can do, we have a pan of water. And in the pan of water, we have an inverted bottle. We used to use in the old days when there were no safety standards. You know those old green Coca-Cola bottles? We used to use those. So they have nice thick walls and they can stand pressure because they bottle Coca-Cola under pressure. We used to take a green Coca-Cola bottle, you fill it up with water, and you suspend it in here in this pan of water. And then you have tubing. So you've got all this sealed up, but you've got a rubber stopper in the top, you've got a glass tube coming down through here, and you've got tubing coming out of here, going up into here, and when the gas comes out, it bubbles into that and forces the water out because hydrogen is not that soluble in water, and you call this collection of a gas by water displacement. And then when it gets full, you take it, and what we used to do, and students don't do this anymore, is we used to take that bottle, have a really long match, hold the bottle around on the other side of a door to protect ourselves, and put the match to the top of that bottle, and we'd have this huge explosion and flames shooting out. We had a flamethrower like 3 or 4 feet long there. It was great fun, great fun. And we didn't even have safety glasses on. on YouTube. I'm sure you can find fools doing the same kind of things. So, anyway, we're collecting it by water displacement. Now let's go back over to the serious part. See, all they tell you is, hydrogen was collected over water. Well, this would be the setup they're talking about. And they're saying it's at 21 degrees, and let's make that 3.6 by giving ourselves a 0.0. When the atmospheric pressure, and this would be total pressure, is 748 torr. Okay, and the volume of this gas bottle, after we force all the water out of it, is 300 milliliters. Okay, now, we have to make some assumptions. First of all, the temperature being 21, the room temperature is 21. If this bottle has been sitting out in the room, the gas has been sitting out in the room, the water here has been sitting out in the room, we can assume the temperature inside is also 21. Okay, we've already measured the volume of this bottle, so we know it holds 300 mils. No problem with that. Okay, now, when you're filling this up, let's say you stopped, the water level inside is higher than the water level outside. What does that tell you? See, there's a certain pressure. Forget about this for a moment. There's a certain pressure inside this bottle due to the hydrogen. Move it around, hitting the sides. There is a certain pressure hitting the sides out here, hitting the water. So we have an inside pressure, we have an outside pressure. If this water level is higher inside than outside, what does that tell you about the pressure? Are they identical?
No.
No. Marco, what does it tell you?
Pressure inside of the bottle is lower.
It's lower, exactly. Okay, now, other case. What if the water level inside is lower than the water outside? What do we know now? Pressure is higher inside. Okay, so when we end this experiment, we're going to be absolutely sure the pressure, the water level inside is equal to the water level outside, so we can say that. And we mark it on the neck, and actually you measure the volume after the fact, where you marked it on the neck. Is everybody with me so far? Okay, so here we can say pressure inside is equal to pressure outside. So that's how I get that, by reading the room's pressure, the barometric pressure in the room, or looking it up on the internet to see what the pressure in Houston is today. And of course they're not going to give it millimeters, but hey, we can switch it. They're going to give it inches. We can switch it to millimeters, which is turning it into torr. Okay, now, where does Dalton's law come into all of this? When you take that, that is the total pressure. That's the outside pressure, and it is the inside pressure. But inside of that container, when you collect over water, whatever temperature you're working at, there's going to be a little water vapor in there. Because at any temperature in the lab, a little water will evaporate. So this is really the sum of those two gases. We're going to assume we forced all the air out. There's no air in there. We forced out most of the water, but we forced out the liquid water. A little liquid water evaporated. So when it says the magic words, collected over water, okay, what we have to do, let me just show you in the text. And this is available. You do not memorize this stuff. I make you memorize enough. Let's see if I can get that table. It is on page 425. And what it tells us on page 425 is the pressure of the water at all these various temperatures. And so what temperature are we working at? 21. Okay, it says the water contributes this much. Now, in the problem, I think it rounded that perhaps to 19 instead of having that many decimal places. Do you see? Doesn't it make sense? If you're working at a higher temperature, more water is going to evaporate, and more water, more pressure in there. And so you have to look it up. Okay, so let's say you don't have that available on test day, but it's going to be in the problem. Okay, and let's see where it is in the problem here. Oops, I got the wrong problem. That's, well, what did I do here?
It was for
12.
that
I must have
12
taken it away over here. Yes, I did. Okay, 12:19. Let me go ahead and show all of this. Because right here is what they would have taken off the table. Because it's saying the pressure of the water at 21 is 19. Now, if you have a really good memory, on the table it said 18.98 or something, but they've rounded it to 19, close enough. Okay, so let's come over here. I know this is the temperature of my gas. I know this is the volume of my gas. But I need the pressure just of the hydrogen. So when you have a problem like this, before you kick in using one of those equations, you got to take care of Dalton's law. And so what that means is, put in 19 torr plus your pressure of your hydrogen. So your pressure of your hydrogen is going to be this minus the 19. Okay, so what's my pressure of my hydrogen going to be? 729 torr. Good. Once you do this, I want you to forget that forever and ever. Make that your first move. When it has those magic words, collected over water. Before you do anything, subtract out the vapor pressure of the water and then go with it. But that is about the only way we use Dalton's law. Take out the water vapor. Okay, now let's try to paw through all of this stuff here. Okay, let's go back to the top. Because this one is always long to read, so it looks overwhelming. Okay, so we have hydrogen was collected over water at 21 on a day when atmospheric pressure was 780 torr. The volume of the gas collected was 300. Okay, here's where it's saying, how many moles of hydrogen were collected? Don't even look on to part B. Just look at A. How many moles of hydrogen were collected? So you ask yourself the basic old thing. Do you see changing conditions? No. So we know right away, it's this, it's this, it's this. But there's something missing. So which of these equations do we need to use? They want to know moles of hydrogen. So what's our choice in the rundown there? 5. So we need to do for part A, PV is equal to nRT. Okay, pressure, remember? That's poison. We don't want it because you've got to subtract out the water vapor.
How did you do that again?
Just subtract.
Oh, okay.
See here, I could put
I missed where she
here. Nina, I can make it look a little bit easier. Let me take out a line. So to get the pressure of the hydrogen, it's just going to be that minus that.
Where'd you get the 19 from? I think 14 part.
The table.
Oh,
The
okay.
table.
Okay.
It was in the table, but here in the problem, it gives it right there.
Oh, okay.
It's usually the last line of a problem. And you might look at your review for test 3. I think the final problem there has one almost identical to this. Okay, so we have 729. Do I leave it as 729?
No, make it ATM.
How do I make it ATM?
Divide by 760.
Divide by 760. Okay, 300. Do I want it 300?
No.
No, Tran, what do I want it?
300 liters.
What do we need it in? You told me no, you didn't
Oh,
want it.
it's in
Liters. What is it in liters? 300 liters? You may be saying it, I'm just not hearing it. 300 mils, how many liters? I know it's getting late, it's in the brain dead. So
0.3.
0.3. And then we can solve for N. We know R. And temperature, 21. Do I want 21?
No.
What do I want, Meredith?
You want it Kelvin, so it's 294.
294 Kelvin. And then we're going to carefully punch this through, and we are going to get, does anybody have moles without looking at my notes?
Yeah.
0.02.
Yeah.
0.012. What'd you get, Meredith? Do you have another SIG, Andrew?
Y equal 0.0119.
What was the digit after the 9?
2.
Okay, let's go with that. Keep 3 6. Sarah, is that what you got?
No,
Well, Nikki.
I got 019. Yeah, I got
not 2.
Oh.
0.0119.
Okay.
Yeah, 0.0119.
0.0119.
Sorry.
Now, you okay? Okay. I probably heard that wrong. I'll take the hit for that one. Okay, so that is moles of hydrogen. Okay, now part B, if we survive that. See, it's nothing new except Dalton's law right up front. Subtract out the water vapor. Okay, part B. I'd like to know how many grams I have. Hey, this is back in chapter 2. If I have moles and I need grams, what do I do with the formula weight?
Multiply.
Multiply. So we'll have, what's the formula weight for hydrogen? 1. I don't think so.
2.
2. Diatomic.
Yeah.
That's why it's super critical to know what's monatomic and what's diatomic. So we've got 2 grams per mole. Moles cancel. Everybody catch that little very, very common mistake? When I say what's the formula weight for hydrogen, just shout 1. But we're not working with hydrogen atoms. We got hydrogen molecules, H2. Okay, so we get, Sarah, what did you get in grams?
0.0238.
Grams of hydrogen. Okay, everybody okay on that?
Yeah, so the reason why you do 2 is just because it's 2 hydrogen.
Yeah. Just like chlorine. If I have chlorine gas, I would not use 35.5, I'd use 71, 2 times it. So, steer clear, be careful, diatomic stuff. Okay, we got about a minute to go. Part C. What if we wanted to know the volume of SDP so we could compare our work with somebody else's work? If I say, what's the volume at STP? Do you see changing conditions?
Yes.
Yes. Okay, so this was part A. That was just, we have a missing part. This was part B. How many grams? No problem. Now, part C.
Okay, why do we use that instead of just plugging in like 1
You don't
for
have
instead of using
enough
program?
Okay, you know the pressure, let's see, you know the pressure, but you know the volume at some other temperature.
Okay, I wasn't sure if like for the program, I wasn't sure, or the STP on number 4, I wasn't sure if like we just plugged in like 1 for the pressure, left the volume.
We will for
Okay.
V2.
So, anytime it adds for STP, we always use that.
Okay, if you're not already working at STP. See, here's, let me go ahead with another minute, at least we'll set this up. Let me just explain. If they say, for part C, volume at STP, we're in the laboratory. We're working at 21. This is the volume when you're working at 21. This was the pressure when you're working at 21 degrees Celsius. Okay, and this is the volume with this condition and this condition. Now they're saying, what would the volume have been if you were in a laboratory that was exactly standard? So I asked the question, do you see changing conditions? And people said, yes. Okay, that means this is what we need. Okay, so real quick, let's just set it up. These are all the ones.
But we have to change.
STP is all the twos. That's where it's changing it to. Okay, just shout it out, and then we'll finish up. It'll just take us a minute. What's the volume initially? Okay, do we have to use liters? No. Here, open season. Let's just use 300 mils. What's the pressure? 729. It's okay to use that. Open season with this equation. What's my temp? Not 21.
Down.
Okay, so why do you still use that later on the top?
Because
There's a possibility of it being zero and you can't divide by zero.
yeah, very good. Very good. Gotta think Kelvin.
So no matter what.
Because over here, in fact, it's coming. Here. What is V2? What's standard pressure in the appropriate units? 760. Good. Hang in. What's my temperature at standard conditions? 273. Okay, Meredith.
Okay, it can't be zero.
Can't be zero. Division by zero is undefined. We'd be out of a problem and we'd take our break. Okay. Which is what you would hope for. Okay, and I think you can manage all of that. Let's take our break. So at 11:32 we'll come in and we're going to start. Is that fantastic? I just finished all of our material with only 2 minutes overtime. I'm a pro. Okay.